Chapter 2.4, Dividing Polynomials, the Remainder and Factor Theorems. So in this chapter, we'll be going over using both long division and synthetic division to divide polynomials. We will be doing this in order to help us start to find zeros, which is the topic of the next chapter. We will learn the remainder theorem and the factor theorem to help us as well. But to begin, do you remember long division? So long division of numbers is something you've probably seen long ago when you first started learning about different types of operations. Here we have written 178 divided by 3, or in other words, 178 over 3. We would write in long division terms as 178 under a sort of L-shaped operation, and then 3 on the outside. So this tells us 3 is what we're trying to divide into 178. So our first step in doing long division is to look at, does 3 go into 1? Which we know it does not. But does 3 go into 17? Well, not evenly, but we can multiply 3 by a number to get close to 17. So 3 times 5 is 15, which is as close to 17 as we can get. So that means that is going to be our first part of our quotient being the actual divided out version of this problem. So we put 5 on the top of our long division, and we subtract off the 15 from the 17 to get 2. Once we have our 2, we bring down that 8 that we've kind of been ignoring, and so we have 28 left over. Now, next step is going to be looking at that 28. Does 3 go into 28? Well, again, not evenly, but 3 times 9 is 27, which is pretty close to 28. That's as best we can do. So if I stick a 9 on the end, we now have a quotient of 59. I subtract off my 27 from the 28, and I have 1 left over. So that 1 is going to be called our remainder. We can consider this answer 59R1, 59 remainder of 1, or 59 and 1/3, either way is okay. Essentially, it is a sum. It is the sum of 59 plus 1/3, or we can use what's called the division algorithm to write it out. So the division algorithm is the dividend equal to the divisor times the quotient plus the remainder. So in this case, we would write it as 178 is equal to 3 times 59 plus 1. But we can alternatively say that 178 over 3 is equal to 59 plus 1/3. Either is an okay way to present our answer, but if you're asked to present it using the division algorithm, it would look like this. Either way, it gives the same information, though. So, now let's apply that to polynomials. If we have the question 2x squared minus 4x plus 2 divided by x minus 3, or in other words, we would have been given something like the following, and we are trying to do division. So the same way as we had 178 over 3, we now have 2x squared minus 4x plus 2 over x minus 3. Well, in this type of problem, just like with the numerical long division, we started by looking at the 1, and then we moved on to the 17. We didn't look at 178 as a whole, we just looked at part of it at a time. That's how we're going to look at our polynomial as well. We will start by addressing the highest powered term. So 2x squared, here is the highest powered term. We've written our terms in order. That's how you should always write it for a problem like this. If it's not given in order, reorder it. So 2x squared is the highest powered term in our dividend. So we look at the 2x squared, we look at the x of our divisor, and we just want to compare, how do I get from x to 2x squared? Well, I can multiply my x by 2x, so x times 2x equals 2x squared. And so in the same way that on the left side I did 3 times 5 equals 15. So I place my 2x as part of my quotient, and now I'm going to subtract off 2x times my divisor. But notice that it's 2x times the whole divisor. Even though I sort of ignored that negative 3 for the moment, I'm still multiplying the 2x by the entire divisor. So 2x squared minus 6x. And then I subtract it off. So that minus is going to get distributed to both terms to get the following. So when we distribute, I now have 2x squared minus 2x squared, so that goes away. But I get a positive 6x because it was negative, so it becomes positive. Negative 4x plus 6x is 2x. And now we're at the step over here where I had to bring down my 8. So I bring down my next number, my 2, to get 2x plus 2. From here, I repeat my steps. So I look, how do I get from x to 2x? Because 2x is now my highest powered term. So from x to 2x, x times 2 equals 2x. So I get a 2 in my quotient, and I subtract off 2 times x minus 3, or in other words, 2x minus 6. So when I do this, I'll get negative 2x plus 6, which cancels out 2x minus 2x, but now 2 plus 6 is 8. And at this point, I can't get from x to 8. There's nothing I can do to get from x to 8 in the same way there's nothing I could do to get from 3 to 1 over here. So 8 is my remainder. So thus we can say 2x squared minus 4x plus 2 over x minus 3 is equal to 2x plus 2 plus 8 over x minus 3. Or 2x squared minus 4x plus 2 is equal to the divisor times the quotient plus the remainder, or x minus 3 times 2x plus 2 plus 8. Either way, you're giving the same information. It's just that the second way is a bit more formal. It uses the division algorithm, and we'll kind of see why that's important when we look at one of our theorems later on. But for right now, just understand that these do mean the same thing. The only difference is that if I multiply both sides of this equation by x minus 3, it would end up being the division algorithm. So it is saying the same thing. It's just a different way of presenting it. So what is the division algorithm more formally, though? The division algorithm states, given a polynomial dividend f of x and a non-zero polynomial divisor d of x, where the degree of d of x is less than or equal to the degree of f of x, there exist unique polynomials q and r such that f equals d times q plus r. Alright, so that's a lot of words. Q is our quotient and r is our remainder. We can kind of see that from my color scheming. But what does all of that mean? Essentially, it's saying if we're taking a situation where we have a dividend that is a higher degree than our divisor. So we have the, right here, the 2x squared minus 4x plus 2 is a higher degree on top than on the bottom. So that's what allows us to do division. In the same way that 178 over 3 is something I can do long division on, but 3 over 178 wouldn't be super helpful. I could do this if I really wanted to get a decimal approximation, but it's not really what we usually use long division for. So that's the same thing here, where we're really only going to use our polynomial long division if we're starting with a higher degree on the top and a lower degree on the bottom. Then what we get out of it will be a quotient and a remainder, where our remainder is strictly a lower degree than our divisor. So in this case, I mean that our 8, there's no way to get from x to 8 because 8 is a lower degree than x, in the same way that there was no way to get to 1 from 3 without dividing. There's no way to multiply 3 by a larger number to get to 1. However, the remainder is either going to be equal to 0 or has, again, degree strictly less than our divisor. But if the remainder is 0, then we say d of x divides evenly into f of x. Or in other words, our divisor divides evenly into our dividend. So, well, essentially, that is, d of x and q of x are both factors of f of x. So, for example, 178 over 3, we knew that this was 59r1. But if instead I was doing, let's say, 36 over 3, this is equal to 12r0. Or in other words, just 12. So, 3 and 12 are both factors of 36, since 3 times 12 equals 36. Writing it like this is a division algorithm, because it's essentially, we're just leaving off that plus 0 remainder. So, that's what this is saying, is that if we get a 0 remainder, then we have a factor. So, we can use this polynomial division to help us factor our larger polynomials that maybe you don't know how to factor as easily as you can a quadratic. Now let's go through another example. Here I have 4x to the fourth plus x cubed plus 3x minus 1 over x squared plus 2. In this case, we want to notice that when I wrote out the actual long division, I added something that isn't there in the original written form. So we've got our 4x to the fourth, we've got our x cubed, we've got our 3x, we've got our negative 1, but what is this? This 0x squared. Well, anytime a degree term is missing from our dividend, we have to include it anyway when we write out our long division. So we start from whatever the highest degree was, which is x to the fourth, and we write every power down from there down to our constant. The reason we do this is because it's basically for organization. So you'll see what I mean by that in a moment, but essentially we need it so that we can line up our work. So we're going to divide by x squared plus 2. So first step, just as before, I look at my x squared, I look at my 4x to the fourth, and I want to know, how do I get from here to here? Well, x squared times 4x squared equals 4x to the fourth. So 4x squared is going to be the first part of my quotient, and I multiply that by the entire divisor, so I get 4x to the fourth plus 8x squared. But notice, I didn't put the 8x squared under the x cubed, because remember that if we go back a few slides, remember that we're lining these up so that we can actually do addition, subtraction operations. So if we have a situation where we're not lined up, where we have x cubed plus 8x squared, I can't really add those because they're not like terms. So instead I have to line it up with the like term of the x squared. But if I hadn't written that 0x squared there, it would have nothing to add to. It would have no like term to work with. So that's why we place that there. Then finally, again, remember we always have to subtract everything off, so we are distributing that negative, so it's minus 4x to the fourth minus 8x squared. To get, again, bringing all of our unused terms down, x cubed minus 8x squared plus 3x minus 1. And now we repeat. How do I get from x squared to x cubed? Well, x squared times x equals x cubed, so that's how we get from here to here. So our next term in our quotient will be x. So I add in an x to my quotient. Then I multiply. So I have x cubed plus 2x, and again lining up my x's here. And then I can subtract. So that will allow for the cancellation of my x cubeds. And then I'll have 1x left over with my 8x squared and my negative 1, or my negative 8x squared and my negative 1. Finally, our last step will be getting from x squared to negative 8x squared. So of course, x squared times negative 8 is how we get negative 8x squared right here. So that negative 8 is going to be the final term of our quotient, like so. And when I subtract it all off, I get this cancellation, and I get a plus 16 to end up with x plus 15 as my remainder. Now, yes, there's still an x left over, but that's okay, The remainder just has to be, by definition, a lower power than the divisor. The divisor started with x squared. X is a lower power than that, so that's okay. It could have just been 15, but it can also have x. If we had been dividing by something with x cubed, our remainder might have an x squared in it. The point is that I don't have a way to get from x squared to x without dividing. There is no x squared times something nice to get me to x. So we write our final answer out as 4x to the fourth plus x cubed plus 3x minus 1 over x squared plus 2 is equal to 4x squared plus x minus 8 plus that remainder of x plus 15 over x squared plus 2. Or we can write it in our division algorithm as 4x to the fourth plus x cubed plus 3x minus 1 is equal to our divisor times our quotient plus our remainder, which I'm not going to read out again. Now, another possibly simpler way to go about this with very specific requirements is called synthetic division. So our first polynomial division problem that we did back on a few slides ago looked like the following. So we've already gone through this. I'm not going to go through it again. But I'm going to simplify it. I'm going to get rid of a lot of the parts of this. I'm going to get rid of the x's and the first terms and all of that, and we're just going to look at it looking like this. And you're going to wonder, okay, but why? And that's a fair question to ask. I will show you, but we're kind of working backwards here. Essentially, we're going to simplify this process by writing it in the following way. This is called synthetic division, and it only works if your divisor looks like x minus k. So remember, our divisor looked like x minus 3. So it is in the right format. Okay, but what's going on here? This is completely random looking, probably. Like, we can see all of these numbers are there, and they all came from that polynomial division, but why did I place them the way I did? How is this helpful at all? Well, now let's start from scratch. So here I have my polynomial long division, but again, what I'm doing, if I don't have all of this information, I haven't done any of this, all I have to work with from the beginning is 2x squared minus 4x plus 2, and we're trying to divide by x minus 3. I start from there. Step 1 is going to be to line up the coefficients in the dividend, making sure to include any zeros, just like we did in the previous polynomial division problem. So in this case, the coefficients in the dividend, the blue ones, are 2, negative 4, and 2. So that's just step 1. So we can see that here, before we even write, we never have to write this. We just go 2, negative 4, and 2, making sure that we're keeping any positive or negative signs. Step 2, we note k in the corner. So remember there's this little corner here. We're going to write k there. Remember that k is coming from x minus k. So we are dividing by x minus 3. So k is actually positive 3. So if it had been x plus 3, if this had been x plus 3, then our k would be negative 3. So it's always going to be the opposite sign. Essentially, k is supposed to be the 0, or what makes x minus k 0. So if I plug k into x minus k, I get 0. So that's what we're placing there. Alright, so once we have our synthetic division set up, again, we didn't do any of this work yet. All we've done was set it up based on having one polynomial over another. Now we can go through our next step. First, we bring down the first coefficient. So I take this 2 and I just bring it down below this little line. That's all. No matter what number that was, I just bring it down to the bottom. I don't do anything to it. Next, we're going to multiply by k. So we're multiplying by that thing that's in the corner, and then add it to the next coefficient. So I multiply 2 times 3 is 6, and I add it to the negative 4 to get this positive 2. And then finally, we're just going to repeat. So I repeat that to get 2 times 3 is 6, add it to 2 to get 8. And so, again, This may seem kind of strange, but that is going to be the pattern we're going to use for any synthetic division. And you'll find that it is a lot simpler than having to go through the steps of polynomial long division. It's just not as applicable everywhere because we have this one specification that it only works if we're dividing by something what's called a linear binomial, a specific kind of linear binomial, where it's just x minus plus or minus a number. So it is very related to that polynomial long division, though. We can see where all the numbers came from. Like, these numbers came from the polynomial long division. It's not super obvious why they came that way, but it does work out when we do this method. It will always reflect the long division form. We just are kind of erasing the long division form for a moment. We're not thinking about long division form, even though we're technically doing it. We just don't realize it. So, the remainder is the last number, that number 8, and we use the others as coefficients of the quotient. So, when we write out our final answer, we would say 2x plus 2. We just take whatever the bottom part of under that line is. We have our remainder is the last number, and everything else we just go 1 degree lower than our dividend. So we started with x squared, this becomes 2x. And then we just add each part. So we'll go through a few examples here so you can get more experience with this. So use synthetic division to divide negative 9x to the fourth plus 10x cubed plus 7x squared minus 6 by x minus 1. So we're going to set up our synthetic division first. We start by taking each of the coefficients, negative 9, 10, 7, 6, but there's something missing here. We don't have an x to the first power term, so there's a secret 0x to the first in there, so that 0 has to be included. Then the k value that's going up in the corner is going to be x minus k. So in this case, k is just the 1, not negative 1. So this is how we would set it up. Now we start by step 2 is bringing down the first coefficient. So we just bring that negative 9 down below the line, and that's it. No matter what k is, doesn't matter what that number is, we just bring the negative 9 down, it doesn't change. But now is where we start doing some multiplication and addition. So we start by multiplying by k. So in this case, k is 1, so it's pretty simple. But whatever k would be, we just multiply by k. So negative 9 times 1, and I write it under the 10. And then I do the addition. So I go 10 plus negative 9 is positive 1. Then I repeat. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 0 plus 8 is 8. 8 times 1 is 8 again, and then finally, negative 6 plus 8 will be positive 2. And so, our actual final answer will give us 2 as our remainder, and then we look back at what our dividend was. We notice it was an x to the fourth, so I'm going to start with x cubed, x squared, x, and just the constant, and we stick some pluses between them to clean it up. And so our final answer is going to look like the following. We have negative 9x cubed plus x squared plus 8x plus 8 plus our remainder of 2 over x minus 1 if we wanted to write it that way, or we could write it in our division algorithm form if we wanted. So now that we have that, let's look at the remainder theorem. So if a polynomial f of x is divided by x minus k, as we've been doing, then the remainder is the value of f of k. So why is this? This is a little strange. Essentially what I'm saying is if I divide something by x minus 3, then it's the same, then whatever remainder I get is the same thing as plugging in 3. That's a kind of cool trick, but why would it work like that? Well, again, here's where the division algorithm comes in. So here we have our division algorithm, And let's say our divisor is x minus k, as stated in this theorem. So I'm replacing d of x with x minus k. Then, since our divisor is linear, the remainder is just a constant number, because remember that our remainder always has to be a lower degree than our divisor. So the only thing lower than a linear term, the only thing lower than x, is just the constant number. So it's going to come out as some number r, right? So here we have our remainder is just the number r, our linear divisor is x minus k. If I just plug in k into f, I get f of k is equal to k minus k. Well, that's 0 times q of k plus r. So once that's 0 times q of k, it doesn't matter what that quotient was. R is what's left over. So f of k is equal to r. That's essentially where this theorem comes from. But let's put it into practice, because it still feels a little bit abstract, even if you kind of understand what is going on with this plugging in and everything. How would you apply this to a problem? Well, if I wanted to use the remainder theorem to evaluate f of x equal to 6x to the fourth minus x cubed minus 15x squared plus 2x minus 7 at x equals 2. So if you're asked to evaluate a function at a point, it means plug it in. So you could say, well, f of 2 is 6 times 2 to the fourth minus 2 cubed minus 15 times 2 squared plus, and it keeps going, and okay, and then, well, okay, so 2 to the fourth is 16, and I have to multiply that by 6, and let's say that's a lot. And this polynomial could be very large. The number you're plugging in could be very large. So do I really want to go through the effort of simplifying this? No. So we have a trick to do it. That's where the remainder theorem comes in. So instead of doing this isn't wrong, but this isn't using the remainder theorem. So if you gave me that as an answer, even if it was in simplified form, I would mark you wrong because you didn't use the remainder theorem. Instead, what we're going to do is we are now going to divide by x minus k, or in other words, divide by x minus 2. So I take each of my coefficients, my 6, my -1, my -15, my 2, and my -7, and I put my k value of 2. Notice that it was x minus k. This is k, so x minus 2, but we switch up what the sign is. That can get a little bit confusing here, but you are placing the original k value of 2 into that corner term. So now we go through our synthetic division. Remember, first we start by bringing down the 6, okay? Then we multiply the 6 by 2. 6 times 2 is 12. Then we add, so I get 11. Then we multiply the 11 times 2. So that's 22. Then we add, so I'm going to get 7. Then we multiply 7 times 2 to get 14. Then we add 16. Finally, 2 times 16 is 32, and we add -7 to get positive 25. So this is our remainder, is that 25, and that's the part that matters. By the remainder theorem, f of 2 is 25, and you can check that by going and plugging 2 into our function, but that's kind of annoying to have to do, especially if you don't have a calculator right on you, which, of course, with a cell phone you probably do, but still, on a test or something, if I ask you to use the remainder theorem and you don't have a calculator to work with, well, it doesn't matter. You should be doing it this way anyway. So this is a quicker way to get our answer without having to go through all of that multiplication, which a lot of errors come up when you're just doing arithmetic like that. Now, using the remainder theorem, we can now move on to the factor theorem. So, if f of k equals 0, then x minus k is a factor of f of x. And vice versa, if x minus k is a factor of f of x, then f of k equals 0. So in other words, if I go through these steps, I do my synthetic division, I get 0 as my remainder, that means f of k equals 0, right? But we know that a remainder of 0 means we have a factor. That was part of the definition, or part of the statements we made when we defined the division algorithm. So, if our remainder is 0, we have a factor. But the remainder theorem helps us determine when our remainder is 0. So, we can use this. Show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Then find the remaining factors and zeros. So here, you're told that this is probably a factor, but to actually prove that it's a factor, one way to do it is to use the remainder theorem to do synthetic division. So we're going to set up our synthetic division. Again, we're showing that x plus 2 is a factor. X plus 2 is our x minus k. So it's x minus negative 2. So k is the negative 2 this time, so that's what's going to go in our corner, followed by our coefficients 1, negative 6, negative 1, and 30. And then we go through our synthetic division again. We're getting a lot of practice with that this time. So we bring down our 1. Then we multiply by negative 2. We add to get negative 8. Multiply by negative 2. Add to get, 15. Multiply by negative 2, and now we're at negative 30. Add, we get 0, and that's what we wanted. So that tells us that f of negative 2 equals 0. And by the factor theorem, if f of negative 2 equals 0, we have a factor. So the remainder is 0, so x minus negative 2, or x plus 2, is a factor by the factor theorem. We can then write our function as x plus 2 times x squared minus 8x plus 15. But we're not really done at that point. So x squared minus 8x plus 15 times x plus 2. Because this question then asks us to find the remaining factors and zeros, we know one of the zeros is negative 2. But we just have to factor further, and now we're at a stage we know how to factor. It is a quadratic, and so we should use our quadratic factoring techniques. So, in order to do quadratic factoring here, luckily the leading coefficient is a 1, so we can factor that using our sort of guess and check method or any other method you've learned to do this. And we're going to end up getting x minus 5 times x minus 3. Because negative 5 times negative 3 is 15, negative 5 plus negative 3 is negative 8, so it all works out. Again, if you're struggling with factoring, I'm not going through how to do quadratic factoring very in-depth here, but it is certainly something you're going to need to know how to do. So we can talk about it in office hours, but otherwise you should be studying that on your own. There's practice for it in the book, etc., and I can provide you practice as well. So finally, now we have this. We can say, by the factor theorem, we have all of these zeros, x equals negative 2, 5, and 3. And so that is it for this chapter. Again, the next chapter is going to go even more in depth into finding these zeros. We're going to continue using these facts. So make sure you understand how to do this synthetic division and why these factors give us zeros, but we'll go more into that later.